So after we talked about the t-test for independent samples and the t-test for dependent samples, and again, independent means between subjects, you have different people in each group, and you've got a categorical variable with two levels. And the dependent is within subjects, the same people for each condition. We started talking about what happens if you've got a categorical variable with more than two levels, and that took us to the ANOVA. The analysis of variance allows us to compare more than two groups at one time. And again, it breaks down very similarly. That if we have an independent measures between subjects ANOVA, that means we have a single IV with three or more levels, and the people in those levels are different. We have the repeated measures or within ANOVA. In that case, again, we have an independent variable with three or more levels, and each person within each condition is the same person going through condition 1, 2, and 3, or however many you have. And then we talked about the factorial between subjects ANOVA when you have some people that are basically in both conditions. That you have more than one independent variable, and the people that were within these independent variables are all different people. So the people that are in factor 1 of your first independent variable and factor 1 of your second independent variable would be different than the people that are in factor 1 of your first IV and factor 2 of your second IV. It's basically going to create a 2x2 grid with 4 groups of people, and they're going to be different. We talked with ANOVA, the assumptions are again that we have a categorical IV or IVs and a single continuous DV. That continuous DV is normally distributed, and that normal distribution is not greatly affected by breaking that DV up into the various groups that we're comparing. And the way we check for that is with a homogeneity of variance. And again, homo means same. Generity is basically a reference to homogeneity, basically is referring to is the variance the same in all of your conditions. And the way we test for that is the Levene's test. And the Levene's test, we actually want it to be not significant, because what Levene's is testing is there a significant difference in your variance across your various IV conditions? And if there is a significant difference, it becomes a problem. As long as it's not significant, that significance in the Levene's test is really all we're checking. As long as it's above 0.05, we're good to go. The analysis of variance allows us to compare more than two groups at one time. So in other words, we don't have to do multiple t-tests. And there's several different types. There's the between subjects, the within subjects, and the factorial. One-way ANOVAs are non-factorial ANOVAs, and a one-way ANOVA simply refers to the fact that there's a single IV, single independent variable, it's categorical, and it's three or more levels. The outcome variable is always going to be continuous, and there's always going to be a single DV outcome. The predictor IV is categorical, but there is no limit on the number of categories, commonly known as conditions, groups, or factor levels. However, every time we add additional conditions or factors or groups, it decreases our power, it decreases our degrees of freedom. And we kind of talked about theoretically that just like every statistical technique we've talked about in this class, at the end of the day, what the math is trying to do is partial variance into effect, individual differences, and experimental error. Which means that when we're looking at independent measures ANOVA, we're looking at very similar to the exact same thing that we'd be looking at if we were looking at an independent measures t-test. We want to know what was the actual variance that's being assigned to the actual treatment, in other words, the IV impacting the DV. What is the amount of just error variance, and also within that error variance, how much of it is actually just due to individual differences, because they are different people. And the reason we'd use an independent measures ANOVA is generally if we have an access to a larger sample size, if we're not wanting to have to test and retest people multiple times with our outcome, our DV, or we're worried about how people might be maturing or changing over time because they're taking multiple tests, we would use this method. And it is probably the more often used method in experimental research. It allows us to use random assignment, it allows us to basically make some pretty strong conclusions, and it avoids those maturation and carryover effect issues. The downside to it is it needs larger sample sizes, and it is technically less powerful. The repeated measures ANOVA is going to be used when we may have just not enough participants. We may be trying to actually make overtime comparisons. We're desperately trying to reduce error because we think our effect size may not be that strong. We want to make sure we reduce individual differences, again, make it easier to detect the effect. But even with that, we still have to worry about potential carryover effects. And again, a carryover effect is simply referring to the fact that people are taking that DV, that outcome, multiple times. They're taking it at the end of every condition. So if you have 3 conditions, they've taken that outcome 3 times by the time they're done with their study. Now, the advantage to this is we've removed individual differences from the equation theoretically. All we're looking at now is the effect minus experimental error divided by experimental error, and that's where we get our power boost. Now, with an ANOVA, when we run an ANOVA, all it tells us is that it's an omnibus test telling there's a difference somewhere within our IV. It doesn't say where that is. Which groups are different from each other requires a post hoc test. And they basically serve as act as a series of paired t-tests. Each group is compared to determine which mean is different. And the one we most often use is going to be a Tukey's test, which is basically just going to give us an absolute difference that's the minimum that we can accept to claim significance at 0.05. So again, when we find with a one-way ANOVA, where we have a single independent variable of 3 or more levels, is significant, we're not done. All we know is there's a difference somewhere. We now need to use post hoc tests to find out where those differences are. And again, just a quick reference, there's Tukey, the person that actually created the Tukey test. The other option is we can always do a priori t-test. The disadvantage here is that it is less successful at actually estimating the error, the p-value, and we should only use those if we have a meaningful reason to use them. In other words, a priori means before we ever ran the statistics. We have a theoretical reason to use a t-test instead of a Tukey's test. And usually we'd use this if we have multiple conditions, but we really only care if 2 of those conditions are actually different. That might be the time we'd use an a priori t-test. If we do use multiple t-tests, more than one, we need to do a Bonferroni adjustment, and we briefly talked about that as well, that when you run multiple t-tests, or actually multiple tests of any kind on the same data set, the estimate of whether or not there's a chance of a type 1 error, making a claim of an effect when it isn't there, the whole idea of that p-value is that it is based on us running one single test. If we run multiple tests, each one of those tests has no idea that we're basically going to the well more than once. And if we do that, we're increasing the chance that we actually may make an error. So one of the ways that we get rid of this is we actually run a Bonferroni adjustment, and that's simply we change our alpha by dividing it by the number of tests we're going to run. So our alpha is 0.05. If I was going to run 3 t-tests on the same data, or for that matter, 3 of any tests on the same data, I would want to divide that 0.05 for a new critical test value, a new basically bar, if you will. I now need to see a p of 0.017 or lower in this particular case. So again, if you actually wanted to estimate the type 1 error with multiple tests, in other words, what's the chance of me actually making a mistake, we can use this equation, which is 1 minus the alpha raised to the power of the number of tests, and we subtract that from 1. So A is our p-value of 0.05, C is the number of tests, and for example, if I was going to run 3 tests, 1 minus 0.05 is 0.95, 0.95 raised to the third power is 0.86. 1 minus 0.86 is 0.14. That means that if I ran 3 t-tests, each one with an individual chance of being wrong at 5%, the chance that any one of them actually being found at 0.05 is actually now a 14% chance of error. In other words, I've got an overall error across all 3 tests that any one of them might accidentally turn out to be significant when they aren't, at a 14% chance, not a 5% chance. And that's why we need to use the Bonferroni adjustment. We finally ended up on the 2-factor ANOVA. So all previous tests before the 2-factor, we always had a single hypothesis and a single null. With the 2-factor, we actually have 3 hypotheses. We have the main effect for our first independent variable, we have the main effect for our second independent variable, and we have the interaction between both factor A and factor B, our first independent variable and our second independent variable. Finally, I just want to remind you guys that around all of this, we need to be thinking about the methodological issues, and the methodological issues include internal validity. Can the causal relationship be made between the independent variable and dependent variable? In other words, is our methods and our statistics and our techniques good? And that includes statistical conclusion validity. Did we use the right test? Did we make the right conclusion? Did we use p-value properly? And then internal validity. Based on that statistical findings, did our methods basically establish causation, or at least a strong argument that the effect that we found was due to what we actually are claiming that it was due to. External validity is once we found an effect, can we actually generalize it from our sample, the people that are in our study, to the broader population of interest? And this involves ideas of both, is it generalizable to the population, but also did we do a good job of bringing our constructs from our lit review into actual meaningful operationalizations within our methodology? So if you claim that you're interested in cognitive ability, but in your methodology, it turns out all you did was a 5-item math test to determine cognitive ability, that's an example of a poor construct validity. You really only got at math ability, and maybe even that not very well, compared to the construct you're trying to claim at, which is generally cognitive ability, which has a lot more factors to it. We also talked about basically the type 1 and type 2 error. And again, the fact that we mainly stack the deck looking for the type 1 error and trying to avoid the type 1 error. And the type 1 error is that when we claim there's an effect that there isn't. And basically by setting alpha at 0.05, we're setting it that 95% of the time we're not going to have a type 1 error. We're only accepting a 5% chance of ending up accidentally in this box. But that does mean that we have a larger chance of a type 2 error, missing an effect that's actually there when we claim it isn't, because we've turned our back on it. And again, this is basically a 2x2 box of looking at the reality, which we don't know, versus what we conclude. In other words, do we reject the null hypothesis and claim there's an effect? If it was true, or whether it was false, is whether we end up in one of these 4 boxes. We also talked a little bit about the threats to external validity, and these include threats to, so this is when we're generalizing, and we basically talked about how the main things we have to worry is about units, treatments, outcomes, and settings. So is there something different about the people that were in our study than the people we're trying to compare it to? So how representational was our sample to our population? Was there something very specific about the treatment itself that would be hard to generalize to other similar treatments? Was there something very specific about the outcome we chose that would be hard to generalize to similar outcomes? And finally, there's the settings, which is basically the location and the time that all studies are going to be confounded. Just because you find it in 1995 in Seattle, would you find it in 2022 in rural Chicago? And finally, we reviewed briefly simple versus multiple regression, with multiple regression suggesting that there are 2 or more predictors, independent variables, and we talked about all of the various forms that we could look at. And again, I really just want you to be aware of what we can do with multiple regression. And what we can do is we can look at linear trends, we can look at multiple independent variables, we can look at covariates, we can look at both continuous and categorical independent variables. And if they're categorical, we're going to create dummy codes to do so. We can look for nonlinear trends, and we can look for interactions. Now, the downside of all this is to look at all of that, we start to come up with a very complex model with a lot of decisions that had to be made. And of course, again, as we make that model more complex, we also start running into issues of power as we reduce the amounts of degrees of freedom, which means we need a larger and larger number of our omnibus tests for us to claim statistical significance. And again, with interpreting the regression coefficients for multiple regression, as we add additional independent variables, we're simply adding those predictors and beta weights to the actual prediction equation. And finally, we ended up talking about the elements of research design, the idea that all elements of research design, the methodology, if you will, of any study, is going to be broken down into how we measure and how many times we measure our dependent variable, our treatments, how we manipulate them and how we add or remove them from samples, our number of samples or groups, do we have a single group, do we have multiple groups, do we have comparison groups, and how people ended up in those groups. Were they the same people within subject design, were they different people but randomly assigned, or were they different people non-randomly assigned? And finally, the amount of time and when these things are being actually introduced or removed from a particular methodology. And we finally ended up with basically briefly discussing actually the notation of research design. And this is an example of that kind of actual notation, where we see R representing random assignment, the first O's representing a pretest, the fact that the top line is group 1, the bottom line is group 2. So group 2 does not get the treatment represented by X, but group 1 does. And then after the treatment has been applied, we measure again a post-test.